In this video, I will show you the control structure for an inverter. So this is the inverter that we will be looking at. So we have one fast leg, which is controlled by a gate signal, and then a slow leg, which is controlled by another gate signal. So we can actually determine the voltage that this inverter generates by choosing the gate signals. So you can see that this is the control structure. So first, we will start at the block closest to the hardware, which is the PWM. So the PWM gets a reference voltage that it wants and then finds the gate signals to realize this reference voltage. So if we look at the inverter, we have a voltage that we want for this one. And then we find the gate signals that realizes this voltage. So that is basically how the PWM works. It just finds the optimal gate signals that you want. So the next block is the current controller, which we have here. So it takes in the reference current and the actual current to find the reference voltage that we desire. So it also takes in other measurements, but they are not as important. I've only chosen to have the most important ones here. So the way that it works, if we look at a simplified model of the inverter, so you can see that this is basically an inverter. We have a voltage source behind an inductor. That is basically how it works. So you can see from this circuit here, it is not hard to find the voltage that would give the correct current. Then we have the power controller. It takes in the measurements, the voltage and the current. And it controls the active power, which is P, and the reactive power, Q. And it controls them separately. So it also needs the power reference, of course. So we need Pref. And then we also need Qref. However, for some inverters, you sometimes don't control the Q, the reactive power. For example, if you have a PFC where you just want a pure active power, you can actually neglect this Q. So sometimes we don't want the reactive power, but sometimes we want it. So you can see that the controllers are after each other. And it wouldn't work if all of them had the same sampling frequency. Because if, for example, the power controller samples at the same rate as the current controller, the reference will be changing before you're able to control the current to the reference, if that makes sense. So in order for this to work, the power controller needs to be slower than the current controller, and the current controller needs to be slower than the PWM. So the PWM is analog, so the PWM is analog, so it doesn't have a sampling time, it is continuous. While the current controller is very fast, it's in the microseconds. It depends very heavily on the application, but it's usually in some microseconds. For example, if you have a switching frequency, which is equal to 50 kilohertz, a common approach is to sample this controller at the same sampling rate as the switching frequency, so 50 kilohertz. So this would mean sampling the controller every 20 microseconds. And the power controller is sampled around in some milliseconds, for example, 1 millisecond. So therefore you can see that this current controller is much faster than the power controller. It's actually 50 times faster, if you see, in this case, but it might vary. So because the current controller is much faster than the power controller, we can actually neglect this power controller when we are designing the current controller. So this method is called cascading, where you have multiple controllers after each other, but with different sampling rates, so they don't interfere with each other. So that is basically how the controller works. So this control structure was a part of a course I'm making on bidirectional single-phase inverters. So it is a course where we look at how to control a inverter. And it works in both directions, so it could be a rectifier and an inverter, but we will focus on the inverter part in this course. So we go through two types of control methods, which is the ABC coordinate, which is basically a stationary frame. It's a simple one. And then a DQ coordinate, which is the one you, for example, use for grid-connected inverters. So here is the block diagram for the control in ABC coordinates. Here is the power measurement. So this is only for active power, as you see. And then we have the power controller, and then we have the current controller, and then the PWM. And here's the control circuit for the DQ. So this is just a way to, so the OSG is basically a way to transform from ABC coordinates to DQ coordinates. Then we have a PLL to find the angle of the grid voltage. And here we have the power measurement, which finds the active power and the reactive power. And then we have the power controller, and then the current controller. And then we transform back to the ABC coordinates. And then we have the PWM. So in this course, I will be explaining both these two in detail and also comparing them. So if you're interested in this inverter course, go to the link in the description.